This question is about enthalpy of combustion. Limonene is found in the skin of citrus fruits. Figure 6 shows a diagram of the apparatus used in an experiment to determine a value for the enthalpy of combustion of limonene. When 1.31 grams of limonene are burnt, the temperature of 60 grams of water in the copper calorimeter increases by 52.1 degrees C. Increases, so delta H is negative, exothermic. Calculate a value for the enthalpy of combustion of limonene. So the first thing is how much heat was transferred to the water. So we had 60 grams of water with a specific heat capacity of 4.18 and its temperature rose 52.1 degrees C. So the first thing you want to do is on your calculator to work out how many joules of energy were transferred to the water. How many moles of limonene did it take to do that? So 1.31 divided by, when you add up, 10 times 12 and 16 ones. So we used 9.63 times 10 to the minus 3 moles to do that. So what was the energy change per mole in kilojoules per mole? So 13066.68, but into kilojoules, so divide it by 1,000 or times 10 to the minus 3, divided by the number of moles that we have. That's coming out as 1,357. But remember that this needs to be a negative number, and I'm going to round it up to 3 significant figures because it was an experiment. So we're going to put a minus in, so minus. So I'm going to put a minus in, and I'm going to round to the nearest 10, 3 significant figures. Table 3 shows values obtained by different methods for the enthalpy of combustion of a different liquid hydrocarbon. Suggest reasons for the differences obtained by each of methods 2 and 3 and the value obtained by method 1 in table 3. So let's look at experiment 2 first. So the value obtained by calorimetry, same way we just did the other experiment, is less exothermic than method 1. Why might this be? Due to mostly heat loss to the surroundings, but also probably incomplete combustion. So quite a different value, isn't it? 1,100 to 4,100. And evaporation of the fuel. All of these things could have affected the answer. And then we've got the value obtained from bond enthalpies. Is less exothermic than method 1. Why might that be? Method 1 being like the Hess law way of doing it. Well, that's due to mean bond enthalpies being averaged over a range of compounds, not specific to these compounds, and being for substances in the gaseous state. It told us this was a liquid hydrocarbon, and we would make liquid water in the a data book value. So mean bond enthalpies is not going to include the energy required for changes of state.